Now that we're outside of the encoder layer, it's officially time for us to break down the differences between the three types of transformers: the encoder-only transformer, the encoder-decoder-only transformer, and the decoder-only transformer. Now, this is where we will briefly modify the graphic that's ingrained in everyone's memory to represent one that depicts an encoder-only architecture. Encoder-only models are highly effective for sequence classification problems, where the entire context of the input is needed to make a single prediction. Think about medical scans looking for malignant tumors, where the input, the image scan or data, is holistic and complete, and the output is a single classification, such as malign or benign. For our example, we can envision that we have an encoder-only model that will classify or predict what TV show a user provided quote is from. How this works is every input actually has a special token prepended to the sequence, the CLS or classification token. Because the classification token goes through the same bidirectional self-attention as every other token, its final output vector ends up aggregating the contextual information from the entire input sequence. This special token, with all the added context and learning from its surrounding tokens, is what is used to make the final prediction. We will frankly ignore the last output representation of all the other tokens, as they were all a means to merely adjust the classification token representation throughout the encoder layers. Let's assume we have 10 TV shows that our model can predict quotes from. Our classification token embedding, which is a row vector of 8 dimensions, will get dotted by a final weight matrix, where each column vector relates to one of our TV show classifications. When we dot our classification token embedding with each column vector, we will get a row vector of 10 scalars. Each scalar is a score reflecting the likelihood of that TV show being the model's final prediction of where the quote is from. As we've seen before, though, we need to compute the softmax of these output scalars so that our resulting row vector adds to 1, and each scalar value can easily be viewed as a percentage likelihood for each respective TV show. Zooming out, you have a complete understanding now of an encoder-only model architecture, from our original input of Beam Me Up to its final output of Star Trek. Now, for an encoder-decoder model, think about use cases that require mapping a single complete input sequence to a different single output sequence. As we've touched on, this was the primary use case driving the Attention is All You Need paper with language translation. Other use cases of the encoder-decoder architecture could be converting from one modality to another. Our input could be an audio file and the output the transcript, or an image and our output some text describing the image. Let's walk through the encoder-decoder architecture with the translation example from English to Spanish. From an encoder-decoder model, the encoder performs its job exactly as before. It reads the entire input sequence, fully contextualizing every token. The key difference is that none of these vectors are discarded. Rather than routing our final encoder output to a linear prediction layer, our encoder-decoder model will pass the entire sequence of contextualized output vectors from the encoder to the cross-attention layer of a separate stacked decoder component. We'll focus on just one decoder block, but just like before, the shape of the token representation is consistent upon entry and exit of a decoder, which allows you to stack as many decoders as you want. Now, the decoder's job is to sequentially generate the output sequence one token at a time. Unlike the encoder, there's no user-provided input to the decoder during generation. So, in order to kick things off, the decoder starts by taking another special token called the Start of Sequence token, the SOS token, and passes it into its first decoder block. Crucially, every decoder block contains a masked self-attention layer. This layer is exactly like the encoder self-attention, except with one vital rule. In this layer, a token can only attend to the tokens that came before it and itself. So, for example, a token at position I can only attend to itself and the tokens at position less than I. This ensures the model can never look into its own future. Let's pause here, though, and explain this, because this is a key difference between an encoder and a decoder. A decoder is autoregressive, meaning the model uses its entire preceding output sequence as context to predict the next single token. So, if I were to sequentially say a few words, starting with I, all I knows about is itself, and the next prediction will be completely dependent on what the trained model would recommend as the next most logical token. Let's assume it's love. Now, just because we now have an input of I love does not mean that we should permit the I token to attend at all to love. The token I existed before, and its contextualized representation should only be based on the past context. If we allow I to attend to love, it will adjust the query key and value outputs of I based on future information, which corrupts the integrity of the sequential generation task and makes the model non-autoregressive. We want I to contribute to the attention based on everything it knew in its place and time, and not be affected by any words that came after it.
Now, decoders only ever pass the last generated token through the model.
So our eventual contextualized love will be our vector that is used to predict the next token U. This perfectly simulates sequential human-like generation, which is the definition of autoregression.
Now, in the decoder of an encoder-decoder model, this mask on the screen will be applied naturally, since we only feed in one token at a time to the decoder. The key and value vectors of the prior tokens are stored in the key value cache, which we'll discuss further later, and the query vectors of the prior tokens are discarded. This will naturally create this mask because there will only ever be one token's query per pass-through, and it will attend to all of the key vectors in the KB cache, plus the appended key vector of itself. We'll see this in action later, but my point is, we don't need to do anything special to apply this mask for the decoder portion of the encoder-decoder model. Where we do need to apply a structural mask is during training, so that we allow our model to train on long sequences of text in parallel, and during the prefill stage of the decoder-only model, which we of course have not yet covered. But let's review how we structurally apply this mask during training and the prefill stage of the decoder-only model, so that when it comes up later, we won't have to readdress this topic.
Masked attention is enforced mathematically by applying a mask to the result of the query.key transpose before the soft attention function is applied to the attention calculation. This mask, which is a lower triangle mask, has a 0 in every index where the row vector index is greater than or equal to the column vector, and has a very large negative number, say negative infinity, for every index where the row vector index is less than the column vector index. This mask matrix is then component-wise added to the resulting attention so that when we compute the softmax function discussed earlier, e to the power of negative infinity is 0. Our 0 value in our mask matrix doesn't affect the attention at all, and the large negative number zeroes out the tokens we don't want to attend to one another. So back to our example. Our initial decoder input starts by default with an SOS token. This initially gets fed through our masked self-attention layer, performing the exact same function as the attention we've already covered. The output of this layer, which maintains the original shape, for us 1 by 8, is then routed to the crossed attention layer, where we will finally encounter our encoder output. Similar to the attention layer examples we've already done, there's still a wait query, wait key, and wait value matrices. To ensure our current decoder sequence attends to the encoder output, we multiply the current decoder sequence embedding by our wait query, asking the question, what do I, the decoder sequence, need? And we multiply the contextualized encoder output embeddings by the wait key and wait value matrices, answering the question, what do I, the encoder output, have, and what will I, the encoder output, give? Now, the only thing to note here is that the attention matrix in the cross attention layer won't be a square matrix like it was for the encoder. This is because our decoder will only ever process a single token at a time, and the cross attention layer will attend to all token embeddings from our encoder. The only scenario we have a square matrix then is if our encoder input is one token, which is highly unlikely. After this is our feed-forward network, followed by add norm. Now, assuming we only have one decoder, just for simplicity, our SOS token will be used to predict the next token in the sequence. Rather than mapping to one of 10 classes, like our example encoder-only model, our decoder will have a column vector and its weight output matrix for each of the tokens in our entire tokenizer vocabulary. With an encoder-decoder model, though, it's standard for the encoder to have a different tokenizer than the decoder, enabling the encoder to hyperfixate on the English context and the decoder to hyperfixate on the Spanish context if we're doing translation. So rather than our weight matrix having 10 columns, it will have 50,000 columns, assuming our Spanish tokenizer has 50,000 total tokens. Similarly, our final tokens vector is multiplied by this matrix, resulting in a row vector of scalar values reflective of the scores or likelihood for each token as the next prediction. We then compute the softmax to see the normalized distribution. As our decoder is autoregressive, the prediction output then is appended to our input and fed back into the decoder as part of the input.
Now, our prior query vector for SOS is discarded. It already passed through the decoder, gathering as much context as it could, and successfully predicted transporta. But now we have no further need for it. This is where we will see the KB cache in action, though, because we don't want to discard the key and value vectors of the prior SOS token. While we discard the query of SOS, we keep the key and value of SOS in memory so that it can contribute to the context of transporta. Not unlike how we leverage the key and value vectors from our encoder to influence our query vector in the cross-attention layer, we want the key and value vectors from prior tokens to influence our new query vector as well. The KB cache is only a function of the decoder, though. It's not needed for an encoder. The encoder's job is a single parallel operation.
It reads the entire input once, calculates all attention matrices once, and then outputs its final contextualized sequence. Since there's no looping or reusing of previous steps in the encoder, there's nothing to cache. Back to our translation example. When we run our new input through the decoder,
The token transporta
attends to the SOS token, which frankly doesn't yield much attention at this point, and works its way through the cross-attention layer where the encoder's key and value matrices maintain the exact same contextual embeddings as they were originally because nothing has changed to the output of our encoder. The next token is predicted me, which is appended to our input, ran through the masked attention, attending to both SOS and transport, works its way through the cross-attention and moves on to predict the next token. Now, we've completed the translation of our input at this point, so in order to stop generating new tokens, our token vocabulary has another special token, the EOS token, or the end of sequence token. When it's a logical point for the generation to end, our model will predict our EOS token as the next most probable token, which breaks the autoregressive loop and stops the generation process. That completes the encoder-decoder architecture. We took a source sequence, English, and converted it to a target sequence, Spanish. But could we simplify the architecture and still achieve the same powerful results? If the decoder is already capable of autoregressive generation using masked self-attention, what if we removed the separate encoder entirely? Instead of routing the input beam me up to a separate encoder, why not simply feed the input directly into the decoder's autoregressive structure? If you make the decoder massive enough and train it on vast amounts of data, the decoder can learn to handle both jobs, the input contextualization job, which is originally done by the encoder, and the output generation done by the decoder. This simplification leads us to the decoder-only model, the architecture that powers modern large language models, unifying comprehension and generation into one single powerful block. Before we get started, though, it is important to note, decoder-only models didn't completely replace encoder-decoder models. With multimodal tasks like audio to text or image to text, the systems used today still involve a specialized audio or image encoder and a text decoder. A simple decoder-only model, regardless of how large or deep, won't perform to par with these complex sequence-to-sequence generation requests without those specialized encoder components. Also, if all you need is a highly accurate English to Spanish translator on site, then you can run a much smaller encoder-decoder model that performs very well without having to run a much larger decoder-only model. So, As we get into the decoder-only model, just keep in mind that decoder-only models are great for a myriad of flexible tasks, whether that be coding or translation or general chat or a myriad of others. While the decoder-only revolution does support some of the original use cases targeted at encoder-decoder models, encoder-decoder models are still preferred for efficient, specialized, high-volume, and mission-critical use cases where flexibility across general-purpose use cases is not required. Now, the decoder-only model architecture has no encoder and therefore has no cross-attention layer. When we remove the cross-attention layer, it looks pretty similar to the traditional encoder-only model, except for 4 key differences. First, there's no classification token needed for the decoder-only model. Second, since there's no encoder, when it receives the input from the user, its first pass through the decoder-only transformer is what's known as the prefill stage. The entire input sequence runs through the model at once, similar to our encoder model, except we now have to structurally apply the mask to ensure none of our sequential tokens can see into their future, maintaining the integrity of the autoregression. Recall that we apply this mask by component-wise adding our lower triangle mask to the output of our attention matrix prior to the softmax operation. The lower left triangle of the matrix has zeros because we want to allow tokens to attend to themselves in their prior tokens, and the upper right triangle of the matrix has negative infinity or very large negative values, ensuring that the softmax zeroes out any identified attention. The mask is only structurally needed during the prefill stage because the subsequent generations will process one token at a time, and the mask will by default naturally be applied. This stage simultaneously contextualizes the entire input and computes the first prediction. Typically, this first pass takes longer than the subsequent token generations, as future passes through the model are only having to calculate the attention of the new token, since all prior tokens' attention will already be stored in KV cache. Third, the output is still not projecting to a classification, but to the entire tokenizer vocabulary. Fourth, the decoder-only model is autoregressive, which, as we've discussed, is the most significant difference between the encoder and the decoder. After the comma is appended to our input, it predicts the next word, Scotty, followed by the next prediction of an exclamation point, followed by the next prediction of EOS, thereby breaking the autoregressive loop. We now have a complete overview of the encoder-only model, the original encoder-decoder model, and the decoder-only model. The main distinction and the key takeaways are that the encoder-only model is for classification use cases, the encoder-decoder model is for translation use cases, mapping the source sequence to a target sequence, such as image to text, audio to text, or English to Spanish, and decoder-only models are for standard next token generation use cases. Thanks for watching.